Today we're seeking positive integer solutions to this strange looking summation expression. Now y'all notice z plus, that just means positive integers. All right, so 1, 2, 3 ad infinitum. And we have an expression here with integer expression lower limit and upper limit. Okay, so we're trying to solve for a and b. Okay, now let's take a look at a simpler concrete case right here so we can see exactly what's going on. Let's say we just have something with actual numbers in it. Let's say I, we'll use I if you want to, I equals to 8, and then we'll make the upper limit 11 here. So we have 11 right here. Okay. Now, again, the part that's slightly confusing about this is just a 1 here. I'll make it even in the Roman sense. That's a 1. We're summing up a bunch of 1s. And so this would be equal to 1 plus 1 plus 1 as we range through the i's here. Now notice this would correspond to I equals 8 right up here, right? I equals 8. You start at 8, right? And you write down a 1. It's a summation simple, okay? Then this would be I equals 9 right above, okay? Sorry, I equals to 9. All right, all the way out to I equals to 11, right? So you can see that this is equal to 4, but a way of thinking of this to give you a formula, this is equal to 4 because you have 4 1s, right? That's equal to 11 minus 8. So you see you subtract the upper limit, or from the upper limit you subtract the lower limit, and then you add 1. Okay? But what does that lead to? That leads to a more general sort of statement here. If you have, let's say, summation I equals 1, or let's make it n. Okay, let's call it n and m. Okay, that's, I think, common. Use it variables for integers. Okay, and you have 1 here. Again, not an I, but a 1. Again, slightly confusing, a little bit of deception here, I guess. This is always going to equal to m minus n. And this is actually a problem from a Vanden Eynden number theory textbook. Okay, they actually asked this question. They listed this expression. They said if m is greater than or equal to n, what it's equal to. You know, and that really helps you understand that summations don't have to have any, the summands don't have any dependency on the index of the summation. Here the index of the summation is I. 1 is just a constant. So you don't see any dependency on I there, but I is still doing some work, okay? So this is just a general formula. Now let's take a look at what that leads to. If you compare it to our original problem, this would be our m, this would be our n. And so you can see this is what we get. We get this expression right here again. Upper limit is a plus b quantity squared. Lower limit is 2ab plus 1. Okay, so we get this a plus b quantity squared minus the quantity 2ab plus 1 is equal to 58. Okay, now notice that this simplifies very nicely to just a squared plus b squared equals to 58. And again, that's, if you're not seeing that, this expansion right here is a squared plus 2ab, right? Plus b squared. So you see you get convenient cancellation here. And we have a and b being positive integers here. Now notice we can make a statement here. A would have to be, A and B both, A comma B, we'll write that down, are integers both less than 8, right? Strictly less than 8. Both of these integers have to be strictly less than 8 simply because 58 is less than the square root of 64, right? So you see, you don't have to guess around too much here. There is some guessing going on. 58 is less than 64, okay? All right, and so anyway, in the square root of 64, of course, is 8, right? Now, so the integers that work out here, there's not many tries. And just by exploring, you'll get that a is equal to 3. Or 7. 7 squared is 49. 3 squared is 9. 49 and 9 equals to the 58, you see. Now, there's nothing that prevents you from just swapping these right here. And then b, and I guess we'll write it in this order if you want to. Right, so the order doesn't matter. We're sticking to positive integers. So these are the solutions, folks. You can swap them around just because of the symmetry. And again, that's not a very formal way of doing it. You could look at 6 squared. That's 36. That's not going to combine to give you anything. Give you 58. You could try 5 squared. That's 25. But 25 plus what is 58? 25 plus 33. 33 is not a perfect square, right? And so these are the only two combinations, 3 and 7. And again, you have to swap those. So these are the solutions, ladies and gentlemen. By trial and error, if this constant was much bigger, it might be more problematic here, but here we can conclusively say these are the answers. The larger the constant, you'd need some more formal way to actually reach the answer. But anyway, that's the final answer. Thank you for viewing.